Okay, good evening. Welcome to the 8224 Exploring Black Holes seminar. I'm Professor Ed Bertschinger, and I'm leading the seminar this evening on the subject of the Einstein field equations. Before I talk about the equations, I want to take a step backwards to a higher level and just ask the rhetorical question of what is general relativity? What is general relativity all about? We've been studying the metric, but if you had to describe general relativity to your parents, how would you describe it? What is it? What does it attempt to do? Speak up, Kevin.
Is that a question?
It really is a question. How would you describe general relativity in one sentence? A simple sentence.
It's a theory of gravity.
Perfect. That's exactly what I wrote down. It is a theory of gravity. Now, the next question, only a little bit harder. What is gravity? What is gravity? Someone else?
The force of attraction between two bodies.
Very good. Gravity is the force of attraction between two bodies. We could refine that and say it's the force that's proportional to the products of the masses and inversely proportional to the square of the distance. But the essential word there is force. Gravity is a force. Yet, if you look on the back of the Exploring Black Holes book, the paradigm for gravity in general relativity is often quite different. Gravity is space-time curvature, whatever that means. Matter tells space-time how to curve. Space-time tells matter how to move. That's a very pithy summary, but it doesn't sound very much like the Newtonian world that general relativity is also supposed to describe. So what I want to do then is to just begin the process of describing how we talk about gravity, first as a force, then as space-time curvature. And we'll make a comparison of the Newtonian perspective of gravity as a force, the relativistic description of gravity as space-time curvature. That will give us the foundation needed to state, at least in concept, the Einstein field equations and say what they describe. Okay. Actually, many physicists have the impression, the mistaken impression, that general relativity so changed our view of the world that gravity is no longer a force, it is only space-time curvature. I think that is a mistaken viewpoint. Just like in quantum mechanics, where one can think of matter as being both particle and wave, or light as being both particle and wave, it's helpful, I feel, to think of gravity as being, on the one hand, a force, and on the other hand, a manifestation of space-time curvature. With that complementary perspective, you'll be able to understand more of the physical content and meaning of the Einstein field equations. So let me then remind you of the viewpoint of gravity as a force. And we'll see that this viewpoint coming from Newtonian mechanics can be carried over to general relativity. In Newtonian mechanics, we write that mass times acceleration is force. Newton's second law. I'm going to put a subscript I on this end because this is called the inertial mass. when discussing gravity, there is a mass factor on the right-hand side that could be completely different, although for some reason nature has chosen that it be the same, m times g. This is the gravitational mass. Galileo, some 400 years ago, established the equivalence of these two masses. This, in fact, is the foundation for Einstein's equivalence principle, a very key ingredient in his theory of relativity and in the derivation and comprehension of the Einstein field equations. This G vector, it's a vector field. Every point in space has a gravity field produced by the sum of all the masses in the universe. Okay. And let's see, now we can ask, what is this gravity field? How do we calculate it? Let me back up and remind you. The content of general relativity is that matter tells space-time how to curve, space-time tells matter how to move. In Newtonian terms, those statements would be mass tells the gravity field what to be, the gravity field tells mass how to accelerate. Okay. A vector whose magnitude gives the magnitude of acceleration, whose direction gives the direction of acceleration for any freely falling body. We'll look at the corresponding equation in relativity in a minute. The other half of the Newtonian description is an equation which says how to calculate G. Well, we remember the inverse square law with attraction. So if we have a mass, I'm going to put an m subscript I because I may have a collection of masses. I'll have a test point x, and then mass points, positions xi. If I take all the masses in the world, calculate the vectors from xi to x, then I can write the gravitational force as a sum over the masses with x vector minus xi divided by the magnitude of x vector minus xi cubed. Okay. Remember, what this ratio does is to take the unit vector in the direction from x to xi and then divide it by the square of the distance. The unit vector is just the magnitude of is just the vector divided by 1 power of its magnitude. That's why there's a 3 in this denominator instead of a 2. Okay, good enough. Let me see if I can use a little bit of this board down here. I want to write this another way, because when I make the connection with relativity, it will turn out that there's another object called the gravitational potential. It's much closer to the key ingredients in general relativity. Mike, if this is not visible to the camera, please bang on the glass and I will lower the boards. In Newtonian gravity, the gravity field, vector field G, can be written as minus the gradient operator of this function phi. And what that means is minus a vector whose components are the partial derivatives of phi with respect to the coordinates. So another way of describing Newtonian gravity is to say that there is a potential function phi obeying a certain equation that I'll write down in a moment, whose partial derivatives give the acceleration. And that equation is, if you like, the Newtonian law of gravitation. It will be the counterpart of the Einstein field equations. I can write it in two forms. An integral form, so the integral form is like taking a sum over masses, but I will replace that sum over discrete masses by an integral x prime minus x like this. So this will be a minus g times the integral of rho of x prime d3 x prime over the distance from x to x prime. Okay. The integral has within it the mass density times volume. That's just the mass that's contained in a little volume, dx prime, dy prime, dz prime. If in this formula I had replaced m sub I by exactly rho of x prime times dx prime, dy prime, dz prime, and made the sum an integral over a continuous mass field, I'd have exactly the gradient of this function phi. I won't show that, but it's not difficult to take the derivatives and actually work out the components and verify it. This is the integral form. Unfortunately, the Einstein equations do not have a comparable integral form solution in general. They have only a differential form of the equations. So if I want to compare with Newtonian gravity, I must compare with the Newtonian differential equation for the potential. You may not have seen it before, unless you read closely some of the supplementary notes, but the treatment here is very similar to that in 802, freshman mechanics, where the Maxwell equations are first presented in an integral form, and well, maybe only in an integral form, unless you take the more advanced version or see a later version of electromagnetism. There you'll find that the electric field can be gotten from a derivative of an electric potential, where that potential obeys almost the same equation as the gravitational potential. This is the differential equation for the gravitational potential. And just to explain the Laplace operator, that is shorthand for the sums of second partial derivatives acting on the potential. Now, this is a lot of math. I could try to describe gravity by saying everything is in inverse square law, but I would not be doing justice to general relativity. Because in general relativity, everything is not in inverse square law. In fact, everything is given by an equation that is deceptively simple. I'll write down the equation for you. It's a lot shorter than the Maxwell equations, but its content is far deeper and richer. And in order to try and give you some explanation of the content of the Einstein field equations, I'm going to be making analogies with the Newtonian equations. Okay, so now I want to take the second point of view of gravity as space-time curvature. This is the standard way of thinking about general relativity. I will show you actually that general relativity can regard gravity as a force as well. But the foundations of the theory are based much more on the geometry of space-time than they are on gravity as a force. The basic law of motion here, I'm going to do this in two parts. Let me just review what I did here. I said matter tells space-time how to curve, curved space-time tells matter how to move. In the Newtonian case, I started out with the second half of that sentence, describing how matter moves in response to a gravitational field. And the answer is that the path a particle takes, x vector as a function of time, obeys a second-order differential equation. Just the acceleration is equal to the local value of gravity computed at that point by summing up the gravity fields of all the masses. The first part, in how to calculate gravity, comes from this sum or from the gradient of the gravitational potential. Now, with gravity as space-time curvature, I'm again going to start out with the second half of the sentence and ask, how does curved space-time tell matter how to move? How does matter move in the presence of gravity? And the statement is this. You'll have seen it in the notes, I think for last week, maybe this week, third set of notes. Freely falling bodies move along space-time geodesics. That is, paths, or I'll say curves, of extremal proper time. Without any equations at all, here is the law of physics that corresponds to F equals ma. Now, we have to introduce a little bit of equations, a little bit of understanding to describe this, the concept of a geodesic, the concept of extremal proper time. This is simply the extremal aging condition. And so what does this exactly mean? Well, a curve is a path, which I will write in this odd way, x superscript mu as a function of lambda. This mu is an index that can equal 0, 1, 2, or 3. It is not an exponent. I don't mean x to the 0th power or x to the 1st power. Rather, x0 is one of the space-time coordinates. In fact, usually it's the t coordinate. x1, if we're working with the Schwarzschild metric, might be the r coordinate, and so on. So this describes the path that a particle takes in four-dimensional space-time where lambda varies along the curve. It is analogous, in the Newtonian case, to giving the position of the particle as a function of time. Now, however, time is one of the coordinates itself, so we can't use time as the variable parameterizing the curve. Okay. A geodesic is nothing more or less than a curve of extremal space-time distance. And in this case, the proper time can be written in terms of this curve in the following way. I apologize for the long equation. You'll find that in the third set of supplemental notes posted at the website. Okay. I believe that something like this shows up on one of the problem sets. Maybe the one due this week, I don't recall. Anyway, this is a way of writing the proper time that it takes to go from point A to point B in space-time along a curve. A curve is a path, parametrized path. Okay. So I have point A, point B, and I have some path from A to B. I could imagine many different paths that go from A to B. The statement of physics is that of all these paths, the freely falling body will take the extremal path. For a massive particle, that in fact means the path of maximal proper time, which may be the path of shortest spatial distance, or it may not. But there's some path from A to B which the particle takes. Okay. Now, how does one actually calculate that path? I've got something that is an integral there, tau. The statement is that if I vary the path, look at all possible paths, the one that has the longest proper time is the correct path that the particle will take. This does not look very much like a differential equation. There is no differential equation here. But it implies a differential equation, as the notes for this week explain. I won't write down the equations in all their generality. I will simply give you the result of applying the recipe presented in the notes to this function and finding the path of extremal proper time. It will look not so different from the Newtonian equation. d squared x dt squared, the acceleration, equals g vector. Well, let's see what the equation is, and then we can compare it. Oh, I'll have to explain some notation in a moment. Okay, so some notation here. First of all, I didn't really say what this g mu nu is. The g mu nu are the coefficients of the metric. g00 dx0 squared plus g01 dx0 dx1 plus, and so on. You actually can work that out from taking the differential of tau, undoing the integral, and then squaring. So there are 16 numbers in here that can be arranged into a 4x4 matrix called the matrix of metric coefficients, or simply the metric. Okay, that's the first bit of notation. In an expression like this, I'm taking partial derivatives of that metric with respect to one of the 4 space-time coordinates. That's a little odd, to say the least, but that's what general relativity gives us. Then I've done another thing in this equation. I've not bothered to write down some summation symbols. Implied outside of this would be a sum from nu equals 0 to 3, a sum from alpha equals 0 to 3, and a sum from beta equals 0 to 3. These are implicit because of the repeated upper and lower indices, nu, alpha, and beta. It's just that if you wrote down all the summation symbols, every equation in general relativity would get about twice as long. So when Einstein first wrote down this equation, about 1916 or so, 1914, actually before he got the field equations, he already introduced what we call the Einstein summation notation that just doesn't bother writing down these summation symbols. So here's some long, complicated expression. But it is very much like F equals ma if we remember that the acceleration is the second derivative of the position. That's analogous to here, second derivative of the space-time position, using proper time instead of bookkeeper time. Here it's bookkeeper time in Newtonian mechanics. And on the other side of the equation, instead of the derivatives of the gravitational potential in Newtonian mechanics, there are derivatives of the metric coefficients themselves. Now, what does this equation really say? Well, it says, as I explained here, that if gravity is the only force acting on a body, that body will take a path of maximal proper time going from event A to event B. And it really is maximum if it's a massive body. If I look at events that are not quite coincident, suppose I ask what's the path that a particle takes for a nearby event, and then maybe goes to some other final event like so. Adjacent geodesics, these are paths of extremal space-time distance. In a curved space-time, geodesics may start out parallel, but then diverge. Or they may start out parallel and converge. For example, on a sphere, suppose that you start on the equator at 2 points that are nearby on the equator but not coincident, and you take the straightest possible paths that you can for each trajectory, going due north. And everyone would agree that due north, if you just follow due north, you end up at the North Pole, and that's the straightest path that you can take. There's no shorter distance between us and the North Pole than by going due north. Two paths at the equator that start out parallel converge and meet at the North Pole. Every single due north trajectory converges at the North Pole. So an indicator of space-time curvature is this property that geodesics which are initially parallel may converge or diverge. Parallel lines may intersect or diverge. That shows space-time curvature. In the language of components of position, this equation looks rather different. In this language, it is analogous to F equals ma. The only difference being that the gravitational force here is given by this complicated expression that depends on derivatives of the metric and so on. Any questions so far?
So that thing's like a gradient. That's
Yeah, these partial derivatives are components kind of like a gradient. I have to say kind of like because the gradient has certain properties that these partial derivatives may not have. So I've described half of general relativity now. I've told you how curved space-time tells matter how to move. All that's left is the other half. How does mass tell space-time how to curve? And the answer is the Einstein field equations. So I'm going to move this board up. And I'll write the Einstein field equations. You'll see they are extremely brief. First, ask the question, how does space-time curve in response to matter? Or, ask another way, what determines the metric? In the Newtonian case, we have the Newtonian laws of gravity. They determine the gravitational potential. There must be some analog in general relativity. And this is the path that Einstein took. He made the analogy. He was forced to modify his thinking about space and time because he realized early on that a proper description of gravity would require curved space-time. And it's not so easy to think about curvature of space and time. The words are longer than the equations themselves. Those are the Einstein field equations. This capital G is Newton's constant. I'm going against the philosophy of exploring black holes book by including Newton's constant, but I do it for comparison with Newtonian equation of gravity, where we retain Newton's constant G, because that's how we learned it. There's another object here, G with superscripts. It has nothing to do with Newton's constant. It's an object called the Einstein tensor. I'll explain a little bit about that in a moment. And then 8 pi, we all know what that is. Although I should tell you that when Einstein first worked with this equation, he wasn't by any means sure whether there should be an 8 pi there or a 4 pi or something else. That was part of his discovery, to figure the coefficient. And the final object on the right-hand side, this team you knew, is called the stress energy momentum tensor? Well, these are just names. What do they mean? What is a tensor? And that's not so easy to explain. Let me start by comparing just F equals ma in Newtonian gravity with the corresponding equation of general relativity. The way that you learned F equals ma, you used a vector sign over, you call it the position vector, the gravity vector. Really, though, what this equation means is a set of 3 equations for each of the components of the vector. So I could write it in components as dx superscript I, or d squared x, I dt squared, is equal to gi, or I is equal to 1, 2, or 3. Those would be called the components of F equals ma. The masses, again, cancel because of the Galilean equivalence of inertial and gravitational masses. Now, this Newtonian equation is very similar to the relativistic equation. At least the right-hand side is almost the left-hand side is almost the same. I've now got 4 components because time is itself part of space-time. We don't attempt to write separate equations for the space and time components. They are together in space-time. And it is the proper time along the path that describes the elapsed time instead of the bookkeeper time. Okay. When I have a set of 4 objects like this, 4 components, in general relativity, we could call those the elements of a vector. In fact, we call it a 4 vector because of the four components. A 4 vector is a tensor with 1 index. Tensors can have more than 1 index. When they have 2 indices, that means a collection of 4 squared objects, 16 objects. The metric itself is a tensor. This collection of objects, g, mu, nu, the metric coefficients, they form a tensor. And so sometimes we talk about the metric tensor. Other times we talk about the metric as being this equation with the coefficients multiplying the dt squared and the dr squared and so forth. 2 aspects of the same thing. So this boxed equation is actually 16 equations written in a very compact way. Still, it doesn't look much like the Newtonian equations. It is, though, completely analogous to the differential form of the gravity equation, Poisson's equation. The only thing different is that factor of 2 on the right-hand side and this object called t mu nu. So I want to talk for a few minutes about the left-hand side and the right-hand side of this equation. We'll see what they mean. Actually, before I do, having seen the summit, the Einstein equations, I want to look down in the valley, as it were, and ask about the content and nature of the Einstein field equations. I started asking the question, what is general relativity? The answer is it's a theory of gravity. Well, now the question would be, what kind of theory of gravity is it? It's not only an equation, a theory with tensors in it. It's a very special theory of gravity, took Einstein a long time to figure out this theory, and it's taken us decades to test the theory. So you shouldn't take for granted. This is not some kind of a mathematical axiom. It's a law of physics, and a law of physics ought to be motivated, it ought to be tested, it ought to be loved. We should identify the requirements for this theory. Now, most of these requirements are self-evident. You think about them very quickly. So I'd like to have a suggestion from the audience of one requirement, of any requirement that a theory of gravity ought to satisfy. Kevin?
Match Newtonian mechanics and low gravity fields.
Okay. I'm going to call that requirement number 2. Reduced to Newtonian gravity for weak fields and slow motions. And they call that number 2 because there's a number 1 that's even more basic and important, I think, and every one of you could state it, I'm sure. What is the requirement for any successful theory of physics? It has to match experiment. Or to put it another way, it must pass all experimental tests. Now, that statement is not vacuous. First of all, it implies that the tests are possible. At an even more fundamental level, it requires that the theory be capable of making tests, of making predictions for tests, excuse me. The theory must be capable of making predictions. And that's something that is very easily forgotten by people. I get lots of letters in the mail, I'm sure Dr. Taylor does too, from people with all kinds of crank theories of the universe. There are many people who think Einstein is wrong. Some of them may be listening on the tape. And the very first requirement that I ask of any theory is that it make predictions that are capable of being tested. Now, general relativity does. And in fact, some of those have to do with the Newtonian limit. But you see, this is even more fundamental because for strong fields, gravity also should pass experimental tests. What other requirements should a theory of gravity, give you a hint, satisfy? A theory of gravity that followed special relativity. Why is the theory called general relativity? I think we had a question in the recitation a week and a half ago about this. What is a concise statement of the relativity principle? The laws of physics must be the same in all inertial frames. That's true in special relativity and in general relativity. In general relativity, inertial frames are only local. They're not global. And so the relativity principle becomes a statement that locally, general relativity must satisfy special relativity. All the laws of special relativity will hold. There are a few other points that are a little subtle. Let me motivate one by asking, in Newtonian mechanics, now I erased one board I'm looking for. You could remember this. What's the source of gravity? What causes gravity in Newtonian mechanics? Mass. Okay. Now, what's the most famous equation of physics attributed to Einstein? E equals mc squared. Mass and energy are equivalent. Okay. Now, in all the rest of physics, including in all of special relativity, different forms of energy are interconvertible into each other and into mass. Chemical energy, nuclear energy, kinetic energy. How about gravitational energy? Well, let's ask about the inverse square law of electrical attraction. When I make a hydrogen atom, I bring together a proton and a neutron into a bound state. Is the energy of that system the same as the energy of an electron and a proton that are separated widely? No, because there is potential energy in Newtonian terms, and that potential energy is negative for an attractive potential. What if you just replace the electrical attraction by gravitational attraction? The only thing that changes is the magnitude of attraction. Would the mass energy of that very weakly bound gravitational atom be the same as the mass energy of the separated particles? Well, it better not be, because then I couldn't conserve energy. I know that to pull apart two particles that are gravitationally bound to one another takes work. And I could get that work by, for example, converting a little bit of rest mass into energy. So the interconversion of mass and energy implies that gravitational fields themselves must have energy. Well, if energy through E equals mc squared is the source for gravity, then gravitational fields themselves must be a source for their own existence. So gravitational fields can induce or modify gravitational fields. The field itself has energy. Now, in this way, gravity is quite different from electricity. Electricity is caused by electric charge. Electric fields carried by photons have no electric charge. So gravity is fundamentally different from electricity. You know, I'm often asked the question, electricity is an inverse square law, so how come I can't just take the Maxwell equations and then replace all the electric fields by gravity fields, and I've got a relativistic theory of gravity? Well, there are a lot of reasons why you can't do that, but one of them is this fact, that gravity itself carries its own source, energy.
And that means you cannot use superposition.
Yeah, technically this means that the equations are nonlinear. Linear superposition does not work. That's a technicality. An important one, but still a technicality. Okay, the last point I will write down, an important one for Einstein's thinking, has again to do with energy. The field equations, or the theory, must be consistent with energy momentum conservation. This really is an aspect of point number 3. Locally, the theory must obey special relativity, and in special relativity, energy and momentum can be moved from place to place. They can be converted. Energy can be converted into different forms, but energy and momentum cannot be created or destroyed without compensation. So this is an aspect of point number 3, but it's an important one. It was in Einstein's development of the theory. He used it as a guide to successful theory. Okay, I'm coming to a close. Got it, probably a couple more boards. I want to talk about the content of the Einstein field equations by explaining the left-hand side and the right-hand side, just giving you an example, a little bit of an understanding of what they are, of what physics goes in here. And I think I will start with the right-hand side, this T mu nu. What is this? Well, it's a thing called the stress energy momentum tensor because it has 3 basic parts to it. One has to do with energy, second has to do with momentum, and the third has to do with something called stress in relativity. First, if I carry this Newtonian weak field concept, I know that in a certain limit, the source for gravity should be the mass density rho. But for consistency with relativity, all forms of energy, not just rest mass, should be a source of gravity. So this T mu nu includes a thing called the energy density U. And for example, this could equal rho c squared for a non-relativistic gas with particles. Rho would be the mass density. C squared gives me conversion of mass to energy. Now, how come the Einstein equation isn't simply that the Laplacian of phi is 4 pi g u? That would be the obvious way of promoting mass to energy and going from Newtonian mechanics to relativity, therefore. Well, the answer has to do with point number 3, locally satisfy special relativity. Energy density is not a Lorentz scalar. Its value depends on your frame of reference. Energy is not a Lorentz invariant. Now, Newtonian mechanics doesn't worry about this because there's no concept of the finite speed of light and no need to consider Lorentz transformations. But relativity has those concepts. Energy is part of what's called the energy momentum 4 vector. Whose elements are the energy and the momentum of a particle. So far, so good. But this energy density is not the same as energy. It is energy per unit volume. And volume itself is not Lorentz invariant. Why is that? If I take a little volume, dx dy dz, a little cube, put little sticks to bound this, and I view this in a moving frame. I ask, what volume does this cube occupy in a moving frame. If I make a Lorentz transformation in the x direction, I have Lorentz contractions. So in a moving frame, if the momentum equals 0 in frame S, then in S prime, U prime is equal to gamma squared times U, where this gamma is the famous Lorentz factor, 1 over the square root of 1 minus beta squared. It ends up getting 2 powers of this gamma. One power from the energy, another power from the Lorentz contraction of the volume. In fact, you'll see why that happens. Lorentz contraction means that this length goes to dx divided by gamma, and it's in the denominator. Okay. The presence of 2 factors of gamma, this Lorentz transformation factor, is what tells us that density, energy density, is part of a 2-index tensor, the stress energy momentum tensor. 2 indices, 2 powers of gamma. Okay? And in fact, the rest of the components of this I'll just write here in a local Lorentz frame. This matrix T mu nu, it's a 4 by 4 matrix. I can split it up into pieces where the 0, 0 component, this would be 0, 1, 2, 3, 0, 1, 2, 3, labeling the rows and columns of the matrix. The 0, 0 component is the energy density. This component is the momentum density. The 3 components along the top row, and also along the column, momentum density. And then there's a 3 by 3 part in the middle that is called the stress tensor. Just to give you a little flavor, momentum density, that's easy to understand. That's momentum per unit volume. It says that if you throw a piece of chalk, on account of its motion, it has a gravitational field. Not the same as the Newtonian one, but a moving mass creates a contribution to gravity, much the same way, by the way, that a moving charge creates an electromagnetic field. In fact, you know that magnetic fields can be thought of as electric fields transformed from the rest frame of the particle. The components of this stress tensor include, very importantly, pressure. It's a 3 by 3 matrix whose diagonal elements are pressure. Why should pressure appear here? Well, look at the energy density. That's energy per unit volume. I'm going to make just a little dimensional analysis and show you that pressure has the same units as energy per unit volume. Energy is force times distance. Volume is area times distance. Distances cancel, and we get force per unit area, which are the same units as pressure. Now, I have to admit, this is not a very convincing argument, but at least dimensionally, it makes sense that pressure could appear in this equation. In fact, there's a more basic reason why pressure has to appear in this equation. It's point number 5. Together, energy, momentum, and pressure participate in the requirements for energy conservation. Because as you learn in thermodynamics, if you compress a box of gas, you do work on it, you apply a pressure, you increase the energy in that box by pressure times the change in volume. P delta V work. So in order to enforce energy momentum conservation in relativity, it is a mathematical requirement that the source for gravity, if it includes energy, also include pressure. Now this leads to some amazing things. For example, it is possible to have substances with negative pressure. Actually, if you take a rubber band, an elastic band, and you pull on it, you have to do work to expand that rubber band. Whereas you take an ordinary box of gas, you let it expand, it does work on you. Releasing a rubber band that's been stretched releases some energy. Compressing a box of gas takes energy. If a substance has negative pressure, it creates a very bizarre gravitational field. In fact, if the pressure is sufficiently negative, the gravity can be repulsive. We think that may be why the expansion of the universe is accelerating. It's filled with a substance of negative pressure. Now, why there's a substance of negative pressure is a very, very big question in cosmology. And we'll be coming to that in several weeks in this class. Last thing. Come back to this board. I've told you about the right-hand side. Just a very brief description of the left-hand side. Bring up this board. This Einstein tensor happens to be, let me see if I can get this right, is up to trivial redefinitions the only tensor that is linear in the second partial derivatives of the metric coefficients. And you need to take a course in relativity or differential geometry to see that. In fact, second derivatives of a metric tell you about the curvature of that space. Just like you may have learned in calculus that second derivatives of a curve tell you about the curvature of the path. First derivative tells you the slope. Second derivative tells you about the curvature. Here you see the second derivatives of the metric. In fact, I have to say it's linear in the second derivatives and contains no higher derivatives. I'm not sure that I have all the precise conditions on the metric here. I'm doing this from memory. I may not even need this second condition. Okay. But that linearity means that in the Newtonian limit, this G00 goes to, let's see if I can get this right, it'll be 2 times partial squared phi partial x squared plus partial squared phi partial y squared. In fact, let me not use, I'm sorry, I just want to, this equation is so nice how this works out. G00 goes to partial squared of the metric coefficient G00 with respect to x squared plus partial squared G00 with respect to y squared plus partial squared G00 with respect to z squared. And I'll check the coefficient in a moment. In this weak field or Newtonian limit. And I will check the coefficient by requiring that I recover the Newtonian equations of gravity. So this is supposed to equal, and I can see there's going to have to be a 1/2 well, no, let me just plunge ahead. 8 pi g times t 0, 0. And depending on my sign of the metric, that will be 8 pi g times u, which is equal to 8 pi g times rho if I pick units where c squared is equal to 1. And I'm going to have to check the sign here. This equation reduces to the Newtonian equation if I'm going to adopt the sign conventions of the textbook, EBH, and put plus signs here. Then G00 should equal to 1 plus 2 times the Newtonian potential. And does it work out right? If I take the second partial derivatives of this object, the set of partial derivatives I have here in these parentheses, this really is the Laplacian of G00. And I will get twice the Laplacian of phi equaling 8 pi g rho. And sure enough, divide that 8 by 2, I get 4 pi g rho. In the weak field limit, Einstein field equations exactly reproduce the Newtonian equation for the gravitational potential. Well, they do so with the implication, with the cost, that the time part of the metric, this is the thing that multiplies the dt squared, is not 1, but it's 1 plus 2 phi. And that means that time is warped. Right? Go back down here. D tau squared is plus 1 plus 2 times the potential times dt squared plus other terms. This is the weak field limit of general relativity. Okay? So it's a funny story with relativity. All of Newtonian gravity that we're familiar with comes from warped time, from the time factor in the metric. All the popular discussion of black holes is associated with the curved space and these funnel embedding diagrams, and we spent so much time already with the spatial curvature. It's the time part of the metric that tells bodies how to fall in a gravitational field. And that's what the Einstein equations are all about. I've gone a little bit over, so I think what we'll do is stop the formal presentation here. But I'll stick around for any questions that you have. And thanks a lot for being attentive. And I'll see you on Thursday in recitation. But if you do have any questions, please stick around.